Hello everyone. Our concentration is on the probability of compound events where we take note of independent and dependent events. Please take note that this is not a developmental lesson, rather this is more of a review in preparation for any evaluation that you might have pertaining to the probability of compound events. We'll be having exercises on determining whether two events that are given are considered to be independent or dependent, the multiplication rule of probability, and you have three examples pertaining to probability of compound events. We'll also consider probability tree diagram. Let's start. You decide whether two events that are given are considered to be dependent or independent. First example, event A is rolling a 6 on a die and second event is tossing a coin. What would your answer be? Independent or dependent events? If your answer is independent, you're right. Second, Mia selects a shirt to wear on a Monday, then a different shirt on a Tuesday. Decide. The answer is dependent events, considering that we already have there the word different. So the shirt on a Monday cannot be worn as the shirt on a Tuesday. Besides, it is always best to change clothes every day. Taking a taxi, event A, and getting a free meal, event B. You decide. And the answer is independent. You can take a taxi without getting a free meal, and getting a free meal does not guarantee that you're going to take a taxi. Therefore, independent. Drawing a jack from a deck of cards and then, without replacing the jack, drawing a 10 from the same deck of cards. What would it be? And the answer is dependent, considering that once you have drawn one card, you do not replace it back. Therefore, the new sample space will only contain 51 cards instead of 52. You choose a red marble from a bag. Set it aside, then you choose a blue marble from the same bag. Decide. And the answer is dependent. Again, you did not place back the first marble. You set it aside, changing now the number in the sample space. Less 1. Let us also take note of, that is the exercises, no? Now, let us also take a look at the rule that we are supposed to follow when it comes to dependent or independent events. Since our clue word here or the conjunction used is the word and, we make use of multiplication, thus the multiplication rule. Let's clarify again. Independent events and dependent events, where, say for example, we are given an event A and another event B. For independent events, A happening has no effect whatsoever on B happening. Also, we can say B has no effect on A, while on the dependent events, A has effect on B. Likewise, B has effect on A. It might be vice versa. But still, we make use of the same formula. The probability of A and B is equal to the probability of A multiplied by the probability of B. Considering again the word and, therefore we can also say that is the probability of A intersection B. Let's take some examples. Say we have this. You randomly select 2 marbles from a bag that contains 15 green, 8 blue, and 9 red marbles. What is the probability that the first marble is red and the second marble is not red, considering this condition that you replace the first marble before you select the second marble? So what is Or how many marbles are there all in all? Let's do the analysis. Total is 32. That is adding your 15, 8, and 9. So all combined, there are 32 marbles. How many red are there? Well, it says in the problem, there are 9 red marbles. How many not red are there? There are actually 23. Not red means we are considering the green and the blue. So 15 plus 8 will give us 23. We consider the event A as selecting the first marble and it is red. And event B is selecting a second marble that is not red. Again, what's the formula to use? The probability of A and B is equal to the probability of A times the probability of B happening. What then is the probability of A? Event A is selecting a red marble. So that is number of red marbles, which is 9, divided by the number in the sample space, which is there are 32 marbles all in all. We multiply this by the probability of event B selecting a second marble that is not red. How many not red marbles are there? There are 23 out of how many marbles there in all, that's 32, because after selecting one marble, we replace it back. Therefore, the number in the sample space was not changed. So we do the operation. 9 multiplied by 23 is 207. And 32 times 32 is 1024. So we can say that the probability of A and B, or the probability that the first marble is red and the second marble is not red, if we replace the first marble before selecting the second marble, is 207 out of 124. In decimal, we can also say that the probability is 202 thousandths, and in percent, we say 20.2%. Again, considering the two events, are they dependent or independent? These two events are independent because the first marble, picked marble, was replaced. Second, considering the same set of given, but this time you do not replace the first marble before selecting the second marble. So still, there are 32 marbles all in all with 9 red and not red 23. Event A is selecting a red marble and event B is selecting a second marble that is not red. Still the formula, the probability of A and B, or the probability of A intersection B, is equal to the probability of A times the probability of B. Recalling the situation a while back, this was our answer. 9 out of 32 multiplied by 23 out of 32 is equal to 207 out of 1024, considering that we returned the first marble selected. But in this particular case, where we do not replace the first marble, then the 32 will be changed into what? Let's see. This now will become the probability of A intersection B is equal to 9 out of 32. Still, that is the probability of selecting a red marble. But this time, the probability of selecting a marble that is not red is 23 because there are still 15 green, and 8 blue. But this time, since one marble has already been taken out from the bag, then we already have 31 only. So the number in the sample space has been changed from 32 to 31. Okay? Because one has already been taken out. So, doing the operations, 9 times 23 is 207. 32 times 31 is 992. Coming up with decimal answer, the probability of A and B happening is equal to 209 thousandths, or in percent, that is actually equivalent to 20.9%. Considering the situation, dependent or independent? The answer is, of course, dependent. considering that we did not put back the first marble that has been selected. That is regarding an example where we did not need to do any tree diagramming. Let us also have an example for probability tree diagrams. Considering the probability that Ramon will pass the board exam is 3/5. The probability that Simon will pass the board exam is 5/6. If each of them takes the board exam, find the probability that A, both Ramon and Simon will pass. That would be very good. Or B, only one of them will pass. What does this mean? It means that it could be the situation Ramon will pass, Simon will fail. And the other case is Ramon will fail and that Simon will pass. There. So what is the probability again that Ramon will pass? The probability that Ramon will pass, let us just rewrite for our analysis, is given to be 3/5. So the question is, what is the probability that Ramon will fail? Considering that the probability of events sum up to 1, therefore we say that the probability that Ramon will fail will be 1 minus the probability that Ramon will pass. Writing that 1 minus the probability that Ramon will pass is 3/5. Subtracting, we now get 2/5. So the probability that Ramon will fail will be 2/5. 3/5 passing, 2/5 failing. That's the chance for Ramon. Let's take that of Simon. What is the probability that Simon will pass? Again, it's given in the problem to be 5/6. So what then is the probability that Simon will fail? Again, we take the probability that Simon will pass, we take that away from 1, we will be arriving at, of course, 1/6. So we will see Simon has a 5/6 chance of passing and 1/6 chance of failing. Let us answer making use of this information. Let us first, before we answer, let us first take or come up with a probability tree diagram. Again, just rewriting the probabilities. So we have here that of Ramon and that of Simon. So what is the probability that Ramon will pass and that Ramon will fail? Passing is for Simon, that would be for a while. It's not 5, but rather, okay, 3/5. What is the probability that Ramon will fail? It's 2/5. Then we take a look at that of Simon. For Simon, the probability of passing and failing will be the probability of passing is 5/6 and the probability of failing is 1/6. But, okay, we also write here that when Ramon will fail, it could still be that Simon will pass or will fail. So, still the same probabilities. Probabilities are not changed in this case because these are two independent events. So that what would the outcome be? So we have that of Ramon. We can follow the outcomes here. We can say, if we follow the first arrow, that's 1, then we will have pass, pass, result. If we will follow up to here, then we have pass, fail. Then, considering these arrows, then we have fail, pass. And this is fail. So, and the last one will be fail, fail. So that is the probability tree diagram for this problem. Now, let us answer the questions based on our probability tree diagram. First condition or first that we have to answer is both Ramon and Simon will pass. So which in the tree diagram are we going to consider? That of the PP because both will be passing. So that we say the probability that both will pass, Ramon and Simon will pass, will be equal to the probability that Ramon will pass multiplied by the probability that Simon will also pass. So following the arrows, we have 3/5 probability, this is it, and the 5/6 probability times 5. So that we arrive at an answer which is equal to 1/2. Again, how did we get that? We have 5 divided by 5 is 1, and then you have 3 and 6 may be divided by 3, so 3 divided by 3 is 1, and 6 divided by 3 is 2, coming up with the answer 1/2. So finalizing that, we can say that the probability that both Ramon and Simon will pass is 1/2. That is 50%. All right? Let's also consider, what about if we have the second one, only one will pass, which would mean to say we consider the PF and the FP. The PF, which means to say Ramon passes and Simon fails. In FP, Ramon fails and Simon passes. So we can then say that the probability now that Ramon passes and Simon fails, we add the probability also that Ramon fails and Simon passes. Okay? So applying the probability rule, multiplication rule for the probability of PF, this is now independent events. So Ramon passes, that would mean to say 3/5 multiplied by Simon failing is 1/6 plus the probability of FP, meaning to say you have Ramon is failing, that means to say 2/5 multiplied by Simon passing, which is 5/6. So that considering, we can now say 3 and 6 can also be simplified. That is 1/2. So we have 1/10 plus, you have again 5 divided by 5 is 1. Then you have here 2 and 6 may be divided by 2. So you have 1/3. 1 times 1 is 1, and then you have there 1/3. So that when we are now going to add, we will be arriving at, I think it would be best if we are not going to simplify because we have here addition. Okay, shall we go back? Okay, let's erase from here. We go over. Okay, there. So we will not be simplifying so that we will be adding faster. So again, we take note for Ramon passing, that's 3/5, and Simon failing is 1/6, plus Ramon failing is 2/5, and Simon passing is 5/6. So we will simply be having the denominator, which is 30, also here 30. All right, so 3 times 1 is 3, 2 times 5 is 10. Considering this, we now have here the answer, which is 13 out of 30. The probability that one will pass, which could either be Ramon or Simon, is 13 out of 30. That is for the first example on the probability tree diagram. Let's take at another example. A box contains 4 white chips and 3 blue chips. 2 chips are picked at random. Maybe place an ender at random from the box, one at a time without replacement. So let's take a look at their probabilities. How many chips are there all in all? That would be our sample space. So n of the chips would be, how many all in all? 4 plus 3 will give us 7. How many white chips are there? We have 4. And how many blue chips are there? We have 3. Right? So let's set up probabilities. Remember, this is considered as dependent events because of the words without replacement. So we consider here, let's come up with a probability tree diagram. First chip, and then we have here the second chip. So for the first chip, the probability that you are going to get a blue, the probability that you're going to get white is 4/7. That is white. What is the probability that you're going to get a blue chip? There are 3 out of 7. So you have 3/7. That is for the first chip. Remember, once you got already the chip, you don't replace it. So for the second chip, if your first chip has already been white, meaning to say there is 1 less white already in the box. Therefore, this would only be 3. And since you have gotten already 1 out, that means to say there are also 6 chips left. Got the point? Then, the second, this is for the white, and then for the blue, inasmuch as a blue has not been taken out, therefore, there are still 3 blue chips, but there are only 6 also in the box, considering that 1 white chip has already been taken out. Now, if your first chip was black, okay, in the second chip, what is the probability that you will still have white? Remember, black has been taken out, therefore, the white are still complete, so you have 4 out of 6. This is for the white. And since 1 black has already been out, that would mean to say that less 1, there are only 2 blue chips in the box. Therefore, you have 2 out of 6, considering that 1 has been taken out. This is for the blue chips. Okay? So that if we will follow, what will be the outcome here? Okay? From the white, and then we have white, blue. Then we have first is blue, then second is white, and the other is first is blue, and then second is blue. So we have these combinations, white, blue, white, and black. That would be the outcomes. Now, find the probability that the first chip is white. First chip is white means to say, in the first one, is the first chip white? Yes. In the second one, is the first chip white? Yes. In the third one, is the first chip white? No. In the fourth one, is the first chip white? No. So we are only considering the white outcome and the white blue outcome. What is the probabilities? What are the probabilities? Let us also write here probabilities. Okay? For white, that would mean to say you have 4/7 times 3/6, giving us an answer which is, let us not reduce it first. 4 times 3, it's 12. Then 7 times 6, we get 42. Then for the white is 4/7 multiplied by, we have for the blue, it's also 3/6. 3 blues in the box. That would still be 12 out of 42. Let us continue the probabilities. Black probability is 3/7. Blue rather. I keep on saying black. It's blue. White is 4/6, giving us 3 times 4 is still 12 out of 42. Then we have black, that would be 3/7 multiplied by 2 out of 6, giving us 3 times 2 is 6 out of 42. Let's check if we're going to come up with a probability of 1 when we add up all the probabilities. 12 plus 12 is 24, plus 12 is 36, plus 6 is 42. So you have 42 out of 42, we get 1. So we have correct. Let me just clean it up. Okay, there. So we take this one. Find the probability that the first chip is white. So we have already said first chip is white, first chip is white. It does not matter what the second chip is. Therefore, we now add up the two. What will that be? That's 12 out of 42 plus you have 12 out of 42. Thus, we now have 24 out of 42. These still may be reduced. What will be our reducing factor? That would be, or divisor, that would be 6. But it's okay if we already have 24 out of 42. So we have 24 divided by 6 is 4, and 42 divided by 6 is 7. So the probability that the first chip is white is 4/7. Let's also take a look at the second question. Find the probability that the first chip is white and the second chip is blue. Therefore, the second chip now is, or matters. It cannot be white, it has to be blue. So take a look at your probability tree diagram, where here is the one that shows white, blue. And we have this combination, white, blue. So the probability is ready, and it is given here to be 12 out of 42, which we can still reduce by dividing both the numerator and denominator by 6. 12 divided by 6, you get 2, and 42 divided by 6 is 7. Thus, we can say that the probability that the first chip is white, the probability that the first chip is white, and that the second chip is blue is 2 out of 7. So there you have it, ladies and gentlemen, examples on probability tree diagram considering both the independent events and dependent events. Thank you again for listening, and let me end up with this. The consequences of an act affect the probability of its occurring again. That is for dependent events considering our life.